So why don't we get started? Welcome to BayBiggies. I'm Jeff, and I'm here with Glenn and Karen, the co-organizers. And tonight we're happy to have Michael Galarnyk here. He's going to speak about speeding up Scikit-Learn training, and he's from Anyscale. I think Glenn did a great job of talking about the Zoom capabilities, but again, think of the Q&A as a way if you want to kind of ask a question that will fit in offline, and raising your hand is a way if you want to kind of interrupt the flow. But be respectful and follow our code of conduct, and kind of keep your discussions to Python and talk related topics. Some upcoming things. So we'll have another meeting in the fourth Thursday of April, which is April 22nd. And we're looking for speakers. If you'd like to speak next month, please let us know. And in general, we're pretty open for speakers. So if you have anything from a short lightning talk to a talk that's like 45 minutes long or whatever is great. Just contact us and we'll work it out. So some other announcements. We have videos up on YouTube. So if you go to BayBiggies video.html, you can see those videos or go to our YouTube channel. I'll talk about this in a second, but I have a little side project I want to announce. I guess before I do that, I want to see, are there any other community people who want to make a community announcement? Let us know. Okay, so I'll do my little announcement. So I've been working on a side project I'd like to get feedback on, and it's this thing called datahut.ai. And what it is a directory of open source software focused on data science and data engineering. So you can see it's kind of organized by a hierarchy of categories, as well as by communities. There's news on projects. And so like if you kind of drill down, you can see data science is divided into a bunch of different topics. And then you can go, and there's some charts and things across that entire area. As well as we can drill down, see like in distributed machine learning, there's Ray. So like there's what kind of a page for an individual project looks like. And kind of the idea is this is a combination of kind of manually curated and editorial content along with some automatically generated content. So, it's a very kind of Python heavy. So in the back end, I'm using, this is obviously a matplotlib. I'm using a notebook to kind of do all the analytics. And then this is actually using Sphinx as to generate the website, the Python documentation tool. So anyway, if you have any feedback, there's a little feedback link here at the bottom, or you can send me an email, but I'd love to get your feedback. I'm going to probably do the real launch of this next month. So it would be good to have some people try it out and let me know if this is useful, or if it isn't, what additional features would make it useful. Okay, I think that's all I have on that. Do we have any other? Okay, no. I get some questions here.
I don't.
Okay, so I see one question from Michael. How do you decide which projects to include? If someone was their project listed, I guess you would contact me. I guess it would, the reason how we pick it is it's in the, how do we pick it? It has to be in the topics we're covering. So we're trying to be kind of a depth focused, not breadth focused site. So it's, really on data engineering and data science. And if it fits in those categories, we might consider covering it. Obviously we have limited resources and we're trying to cover the larger ones, but anyway, I appreciate any feedback.
So I should mention before starting, I'm very open to people interrupting for questions, comments, concerns, and all the above. And I'm really excited to be here today. And the title of my talk is How to Reduce Scikit-Learn Training Time. So before starting, I just want to introduce myself a little bit. So I currently work in developer relations at Anyscale. So we're a distributed computing company. And a lot of my job is actually writing about distributed computing, media relations, marketing, occasionally giving talks. And previous to this, I worked at Scripps Research, where I worked a lot with wearable data. So working with Fitbit data, Apple Watches, those sort of things, and looking at longitudinal trends in heart rate, sleep, activity. And then after I left, they've actually got into working with COVID-related data. So predicting COVID before the onset of easy to see symptoms. Additionally, I also teach at Stanford Continuing Studies. I teach machine learning with Python. I have a couple of LinkedIn learning classes, I occasionally post on YouTube, Medium, etc. So that's about me. So now about the talk. So as far as why you want to speed up Scikit-Learn, Scikit-Learn is a really great, easy to use Python library for machine learning. However, sometimes, like most machine learning models and libraries, it can take a long time to train. So there are a lot of different ways to speed up Scikit-Learn. The first one is relatively simple, and this is not why you probably came to this talk, and that's to upgrade your Scikit-Learn. And there's a lot of recent improvements over time. So one of them is just, release notes. Sometimes there's a new model, sometimes there's an algorithmic improvement, like to HIST gradient boosting classifier. There's polynomial feature expansion. Additionally, there's other things like changing your solver. So better algorithms allow you to make better use of the same hardware. So we'll talk about that. Additionally, there's other things like choosing different hyperparameter optimization techniques. And finally, probably what you might be curious about is parallelizing or distributing your training. So Scikit-Learn by default tends to run on one core. However, typically these days, most computers have more than one core. Additionally, sometimes working on a single node or a single computer may not be enough, so you can distribute your training. So let's first start with upgrading your Scikit-Learn. So it really is just a pip install upgrade Scikit-Learn. And of course, there's a link to various efficiency improvements for various Scikit-Learn releases. This can not only be a really easy way to do things, but it can also give you ideas for improving your workflow. I should note that for all the links here and everything on this talk, I have a link to the slides, and I think they'll be shared in the chat below. And if not, please contact me and I'll be happy to send you the slides. So the first thing to mention, this is just a single example, is that it used to be that some algorithms didn't really have support for categorical features. And in the past, when you had a lot of categorical features, one thing you had to do was to want to hot encode your features. And on the right side of the screen here, we see that the fit times for one hot encoding categorical features for a particular data set used to take a long time, and it would lead to relatively similar performance to other ways of dealing with categorical features that they now have, as well as ordinal encoding and as well as categorical encoding. Additionally, of course, I should also mention this. A great way to speed things up sometimes is you can drop your columns that have categorical features, but that's not really ideal as you're throwing away a lot of information. So in this talk, I'll also talk about not just speeding things up, but also keeping your same performance, or in some cases, actually improving performance, even while speeding up your training time. So just being really quick here on histogram boosting improvements. One of them is when you one-hot encode, what this really means for a lot of tree-based algorithms is that you tend to have more split point string fitting. So this tends to lead to deeper trees. And when you have deeper trees, it tends to take longer to train. So what you see in the graph here, I also want to mention is that there's different ways of encoding your data. So some of this is about encoding your data and about how Scikit-Learn handles your data itself. So if you ordinal encode categorical features, if you have, let's say, I don't know, colors of the rainbow, and you say one's better than another, that's not really ideal for a data set for a lot of cases. So you might want to be careful if you change your categorical features to ordinal and a couple other things. But native handling of Scikit-Learn is pretty good. And while it may not be the quickest fit time-wise, it still gives pretty good performance. It's a lot faster than one-hot encoding. So I also want to mention just another quick feature here before we get into the meat of the talk. And that is fast approximation of polynomial feature expansion. And if you ever work with polynomial features, you tend to have interaction terms. So you tend to have x squared times y. And if you have higher order polynomials, you can have many, many terms, and this can get out of hand really quickly. You can land up with a lot more features than you might have originally wanted. And the problem with this is not just the curse of dimensionality, where you could have too many features and your model won't fit as well. It's also slow, at least with large scale data sets. So we see to the right side here is that when you have more and more features, it tends to be takes a bit longer to train. And of course, if you have more than a couple thousand features, it can take even longer. That's why one addition to Scikit-Learn recently was polynomial count sketch, which is a kernel approximation function, which essentially gives you a faster way to represent a certain polynomial. And of course, anytime you have some sort of kernel approximation, this can lead to a little bit more difficulty interpretability and sometimes some accuracy because it's an approximation. So perhaps one of the best ways to speed up your Scikit-Learn training is by changing your solver. And a lot of machine learning algorithms are formulated as minimization of some function. So you want to typically find the bottom of a parabola in a really simplistic term of a trained set of examples. And optimization functions help with minimization. Of course, sometimes you have problems where you're not trying to minimize something, but I digress. So the idea here and the idea of this talk in general is just about better algorithms for the most part, and better algorithms allow you to make better use of the same hardware. So what you see to the right here is an image from one of the core contributors to Scikit-Learn, and it's from one of his talks. So you can click on the link if you're very curious. And what it essentially shows here on the left-hand side, when you have a full gradient approach where you use a solver like liblinear, convergence happens relatively rapidly, but each iteration through the data. So if you're trying to minimize some function and you're going through your entire data set or your entire training set, each time you go through an iteration, it can take a while because you're using all your data. And I should note here in the image here, when it says large N, that just means number of samples. And so you also have subsampled approaches, and this is just a different solver, where if you have a subsampled approach, this is where you're taking some sampling of N, where each iteration is cheaper to compute, but it can converge a little bit more slowly. And I should mention that there's so many different variations, different solvers for different algorithms. And one of them for logistic regression, for example, is Saga, which kind of achieves the best of both worlds, where you have cheap iterations and the algorithm converges relatively rapidly because of variance reduction technique. And that is solver for Scikit-Learn. So naturally, if you're not familiar with machine learning, or if you're just curious or you just don't happen to know random solvers offhand, let's talk about it in practice, and we'll go into recommendations for which solver to use for which problem. And what the code on the screen shows is that sometimes different solvers suit different problems. And what we have here is a two-class problem where we have n underscore classes equals 2. And we have two solvers we're trying for logistic regression. So we have the same code you normally see where you import the model you want to use. You have some data set, you split the data into training and testing sets, you make an instance of your model, you fit the model in the data. And what this code is basically showing us is the time it takes to train for different solvers. So for liblinear on the same data set, it took 2,400 seconds. And when you went to Saga, it took roughly 133, so like 2 minutes. And I should note that it's not always just about getting the fastest convergence. It's sometimes about the application you have. Just something you can always consider when you program is, are you picking the appropriate solver? Just like, are you picking the appropriate hyperparameters or even the appropriate model for the problem? So again, to note that this code is for single class, not multi-class, as sometimes these algorithms are meant for different sorts of problems. So linear in this case is only meant for not having multi-class. So it's limited to about having 2 classes. So of course, for logistic regression, and I don't want to go too into depth for a single algorithm, but in practice, if you ever use logistic regression from Scikit-Learn, you know that by default, it can deal with multinomial cases where you have more than 2 classes. It typically does this by default. In the code here, I just specified multinomial for pedagogical reasons, so for teaching purposes. And what we show here is going through iterations and seeing the time it takes to converge for these different solvers, Newton, Saga, LBF, GS. So you can see that it makes a bit of a difference. One thing to mention about all these cases for changing solvers, sometimes it's best not to prematurely optimize. So if you have a small data set, as long as your solver works relatively well and you're converging relatively fast, it may not be worth it to tune this as well. It's just for the case where you have a lot of data or solver isn't appropriate for the problem. So of course, naturally, we're not going to know all the solvers offhand. So Scikit-Learn's documentation has a lot of good suggestions on which solver to use for different cases. So for example, some solvers are faster for large data sets, like SOG or Saga. And part of this is due to the subsampling approach of a Saga. So linear is a full gradient kind of approach. So it's using your entire data set essentially for each iteration. So it's not recommended. Additionally, some solvers are good for unscaled data sets because a lot of algorithms require you to scale or standardize your data in some format. So just something to look into and to consider each time you work with Scikit-Learn, especially if you have a problem. And of course, if you have questions right now.
Yeah, Michael, we do have one.
Yeah, sure.
So it's one that actually involves code. So you might want to look at the Q&A button yourself as well. But Jim is asking, basically, I have this snippet where it says from scikit-learn.svm import svc.
Mm-hmm.
And inside of this, he has a snippet of code, which has inside of the SVC class, he has the parameters of gamma equals auto, weight, class weight equals balanced, and probability is true. And he's fitting that with variables X and Y. And he's actually asking, what are his hyperparameter options? And how can he find out how many cores that he has? So
let me answer the latter question first.
Cool.
And I'll come back to the first question. And I actually have a slide that kind of goes into that. So typically, are you on a Mac or Windows? That's the real question here.
Hey, Jim, you want to paste again if you're on Mac or Windows?
Yeah.
Android.
Okay. I honestly don't know how to find out for Android. I'll show for a general case in case anyone has a question. So, and I'm sure I can Google this and come back to you for Android. So my overview of my system, I can look at my system report. I can look at my hardware for a Mac at least. I can see that I have 4 cores here. I can't really zoom in. I can see other things about my computer as well. But for Android, I would have to Google you and come back to you, and I'm more than happy to do so. So with Scikit-Learn, I should also mention, one thing I'll talk about later on in the presentation is there's an njobs parameter for a lot of algorithms. If you want to use all the cores by default, you can do n_jobs equals -1, and I'll create 1 job per core automatically. And as far as hyperparameters, I promise I'll come back to that as we go through.
Great.
So the next thing to consider are different hyperparameter optimization techniques. So if you've done machine learning before, or you're just getting started, one big thing is that to achieve high performance for most Scikit-Learn algorithms, you need to tune a model's hyperparameters. And hyperparameters are the parameters of a model which are not updated during training. So these are things you set before you start training your model, usually. So I'll show an example in a second, and hopefully it can help answer a question. If not, I'm happy to come back to it. So Scikit-Learn by default has a couple techniques for hyperparameter tuning, like grid search and random search. And there's also a couple other techniques that are newer that you may not be familiar with. So just as a quick review, if you know grid search, if you don't, then we can learn together. And grid search is when you exhaustively consider all parameter combinations. So if you're working with, let's say, let me see what the question was for you before. Let me pull up the Q&A. Oh, okay, I can't pull it up. Okay, so if you have a support vector machine and you want to tune your C parameter, C could be, it's a regularization parameter, and that could be like how much you want to regularize your model. That's something you can tune through hyperparameter optimization. There's other parameters for support vector machines, of course. We can go over those if you want later. So there's also random search, and it differs from grid search in the sense that you're sampling a given number of candidates from a parameter space within a specified distribution. So grid search you can think of as just trying every possible combination, and random search is a bit more selective. So grid search then takes longer, and in theory, it'd be more performant if you tried every possible combination. But in practice, grid search can often miss the optimal part of the important parameter. So let's go over grid search a little bit as far as the benefits and drawbacks. So if you try every possible combination of a parameter, it's relatively explainable because you're just trying everything. And a benefit of just trying everything is some of these workflows can be parallelized. And I'll talk about parallelization in a little bit. And there's some drawbacks about parallelization or about grid search. And one of them is that if you're trying everything, it's relatively inefficient and expensive, especially if you have limited computing resources, limited time. So we see that the right is actually not Scikit-Learn code. I just have it here for teaching purposes. And so for grid search, if you have three parameters you want to, hyperparameters you want to tune, let's say like learning rate, hidden layers for neural network, or a different parameter, what you essentially have is a cross product of all possible configurations. You have three different values for this hyperparameter you're looking at, and this one, and this one. So you're effectively looking at 27 evaluations, which can be not too bad as far as modern machine learning. But if you have a lot of different hyperparameters, a lot of different values you're looking at, this can get out of hand relatively quickly. So
could I ask you a quick question?
Yeah, sure.
I'm sorry, I was trying to find a good segue there. Can we ask a question about the Saga solver real quick, or
Yeah,
is
sure.
you want to wait on that one?
Sure,
So
let's
on
see if I
this,
can answer it.
yeah, no worries at all. So does the Saga solver have a larger fixed cost than other solvers, which would make it slower for small data sets? If so, roughly, what's the crossover point in data set size where Saga becomes faster?
So typically for Saga, it's going to be faster for most cases, at least if you have a couple megabytes. I don't know about the fixed cost. I haven't seen the implementation itself. So that's why, like with anything, like when we learn, we teach, I find that I always go back to the documentation anyway to see if there's some reason why something's a bit slower. But typically, if you're working with a couple megabytes, you're not going to notice the difference anyway. It's not noticeable by the user. I think more the issue for me when I work with these different solvers is I need to know that they support things that I'm interested in doing. So if I want to have an L1 or L2 penalty, some solvers limit my behavior of what I want to do. So that's more of the issue than I would say the speed itself in this case. Except for lib linear, which can take a really long time, like a really long time. I hope that answered a little bit.
Cool.
I could look up the implementation and just check to see what the cost is. So one thing I just want to briefly mention, and I can't really go back in slides. So for grid search in Scikit-Learn, it's a pretty simple workflow, relatively speaking, where you first import the libraries you want to use. So in this case, you're importing GridSearchCV. I'm making a data set here, but of course you can import a data set through pandas. You can get a data set from SQL and put it into Python. You have an instance of your model. So in this case, I'm using a support vector machine here, and I have a kernel I want. I'm saying a certain probability. And what I can also do here is I can grid search through my classifier. I can look at gamma range, for example. I can look at my regularization parameter, my C range, and then I can go through and grid search my data. This is a relatively small data set because I only have a couple, like 1,000 samples here, which is, I'm surprised I actually have this on a slide. But it's not that big, and it still took like 2.5 minutes on my 4-core computer. I'm not parallelizing it yet or anything. It just took a little bit of time because I had 9 values for gamma and 9 values for C range. So 9 times 9 is 81. So my model effectively had 81 evaluations for my grid search here. So as far as random search, it's sampling. So the idea with sampling is you're not really testing every possible evaluation in your data set. And so there's a lot of advantages to random search. One of them is that it's really easy to parallelize, similar to grid search. It's also hard to be in high dimensions. And random search is also used for more complicated frameworks other than Scikit-Learn. You see it in PyTorch, TensorFlow. It's pretty widely used as far as hyperparameter optimization. One drawback of this is rather than testing every possible combination, it's less explainable because different parameters have different distributions and so on. So with Scikit-Learn, it's relatively easy just to switch. Instead of importing GridSearchCV, you import RandomizedSearchCV. And when you go through the training process here, it's a lot faster. Recall from before, for grid search, we had 81 possible evaluations we went through because 9 values for gamma range and 9 values for C range. 9 times 9 is 81. However, for random search, for this example, we have 10 things we went through, less configurations. So it's a lot faster because we have 71 less configurations we have to go through. And the performance was relatively similar. So with these sort of techniques, especially if you're just starting, or you're just looking around, I always advise people try things first and then figure out how they work, especially if you're working with a small data set or a little project of your own. Because going through the nitty-gritty of how things work is great for the industry, but if you're just playing with it, just try first, then figure out and as you go. Learn by doing. So more questions before we continue?
No, we're good.
Okay, wonderful. Oh, cool. So by the way, someone asked about number of cores before and Jeff answered for Android. For in Python multiprocessing, you can do .cpu_count, and that's wonderful. Thank you. So it's also very useful if you're working in the cloud, for example, if you for some reason don't know how many cores your instance has. So there's a lot of different optimization techniques, and some of these are a bit newer, so they may not be as well tested. So Scikit-Learn recently introduced having grid search and having randomized search. You can think of this as kind of a tournament style setting where hyperparameters are evaluated as a small number of resources at the first iteration. So in the first iteration, imagine considering a bunch of different candidates for hyperparameter values. And you start with a small number of samples, let's say 20. And then next iteration, you'll end up with double the amount of samples and half the number of candidates, and so on and so forth until the end. And the idea here is you give more resources to candidates that are more promising during each successive iteration. So you save yourself some time. I should also note that Scikit-Learn is a very well-established library and framework. And there's a lot of libraries that can enhance the capabilities of Scikit-Learn. One of them is Tune-sklearn. It kind of acts as a drop-in replacement for Scikit-Learn, among other things. And it provides other cutting-edge hyperparameter optimization techniques like Bayesian optimization, early stopping, and distributed execution. So what we see at the right is hyperparameter set 2, if it happens to be unpromising hyperparameters, at least initially when you first start training, when you start iterating through the data. Tune Scikit-Learn and other libraries can do this as well, maybe not as well. They can detect bad performing trials and stop them early to avoid wasting time and resources. This sort of thing really matters if you're compute constrained, time constrained, cost constrained. You want to spend your compute time on something where it might actually produce results that are more valuable to you. So as far as features of Tune Scikit-Learn, and if you're curious, I can link to a blog post about this library, or you can also Google it as well if you like. One of them that's really important for a Scikit-Learn workflow is Tune Scikit-Learn. All you really have to do is after installing it, it's really the same workflow as Scikit-Learn, where you import, instead of GridSearchCV, you import TuneSearchCV. You also, for Scikit-Learn, import the model you want to use, in this case, SGV classifier. You load some data set, you make an instance of your model, and then you go through a sort of hyperparameter grid, and then you select the search optimization technique you want. You can also specify early stopping, so if the trial is not going well, you can cut it short, saving you time and resources, and so on. It's a very similar sort of workflow. So the other advantage of this is scalability. So with Scikit-Learn, as I'll talk about a little bit later, it's typically meant for a single node, so a single computer, although there are frameworks and libraries that are trying to make it distributed, so more than one computer, which Tune Scikit-Learn can do. So there's a couple other things I want to mention, and I'm trying to be cognizant of everyone's time. And one of the best ways to speed up Scikit-Learn that you may not use in your daily workflow is to parallelize or distribute your training, especially parallelize your training. So what you see on the right here is a single core. So if my laptop that I'm presenting here today is 4 cores, typically for Scikit-Learn, I do things on a single core for a lot of workflows. And this is what you get by default unless you specify n_jobs in Scikit-Learn. So if you specify n jobs, and you can do this, it's done underneath the hood by JobLib, and there was some execution engine with Ray. You can go to multi-cores and utilize all the cores in your computer. So this image basically shows resources that Scikit-Learn can utilize for single core, multi-core, and distributed settings. So naturally, if you use all the cores in your computer, you can speed up your workflow. So on my Mac, I just went to the top left-hand corner of my screen, and I found out how many cores I had, and I have 4 in this case. And since I'm only using 1 core for my default workflows, naturally this computer can use 4 cores, assuming I have the memory to allocate. I should also mention that typically today, virtually all computers have multiple cores. So if you're just using Scikit-Learn on a single core, you have the opportunity to parallelize your workflow. And so this MacBook, of course, is a single node with 4 cores. And if I use multiple cores, I can speed up the training of my model, as I mentioned. So this is really true if your model has a high degree of parallelism. So what we see to the right is a random forest model. And random forests are extremely parallelizable models, as each decision tree that constitutes a random forest in this ensemble model is independent of the others. So when you have your original data set, you typically start by bootstrapping your data. So sampling with replacement. So if I had a jar of marbles, I take a marble out, shuffle my jar of marbles, put it back in. I essentially get different data for each decision tree to be grown from. And then in the end, however many decision trees I have come together to make a prediction. So if it's classification, it's majority vote. If it's regression, it's a mean, and I have a prediction. And this sort of thing can be done in parallel because these are all independent of each other. So Scikit-Learn can parallelize training with JobLib, which by default uses a Loki backend. which is really good for a single node. So working on a single computer, essentially. So I should also mention, though, that JobLook allows you to choose between other backends like Loki, multiprocessing, Dask, and Ray. So of course, Loki is optimized for this sort of situation and not for running on distributed applications. And distributed means more than one computer or more than one node in the context of this presentation. So to incorporate this into your workflow, it really is setting an additional parameter for GridSearchCV, RandomizedSearchCV, etc. And all you have to do is specify n_jobs equals -1. And this can utilize and create one job per core automatically. So what I had before, I believe, for running this on my computer without parallelization for GridSearchCV, it was like 2.5 minutes. And by utilizing 4 cores, I got down to like 37 seconds. I should note that just because you're utilizing all the cores in your computer, if I have 4 cores, it won't necessarily get 4 times faster. There's always some sort of cost for parallelizing workflow, and especially distributed workflow. So let's now talk about distributed application challenges. So this image to the right is one of my favorites. It's from Reddit, I believe. I can check the image source here, but you can check it on your own if you like. So one thing about distributed computing is it doesn't always go the way you would hope, ideally. And there's a couple of reasons for this. One of them is that scheduling tasks across multiple machines can be very difficult. It requires a lot of communication. It requires transferring data efficiently, sometimes sharing memory. There can be a cost if you don't transfer data efficiently enough. It also requires recovering from machine failure. So if one node fails at some point in training, you want to be able to recover. And it's always been a bit of a challenge. So that's why there's the Ray backend, and that can handle the details for you, keep things relatively simple, and lead to better performance. So I like to think that Ray makes parallel and distributed processing work more than like you'd hope, ideally, unless your goal here is to have cute puppies just, eating things everywhere, which is still nice. But for distributed computing, you probably want more of the left side scenario. So what I have here is a couple graphs, and this is just an example of just a benchmark of using different backends, essentially. So there's Ray, there's multiprocessing, and Dask relative to the Loki backend. So what we see here is each one of these colors, the blue here is Loki, the orange is multiprocessing, this lighter orange, I believe it's orange, is Dask, and the gray is Ray. So in this graph, higher is better because it's normalized speed up in terms of execution time. And it's for support vector machines, random search, grid search, and random forest. And of course, the performance is measured on relatively big instances on Amazon on 1, 5, and 10 M5.8x large nodes with 32 cores each. And notice here that the performance of Loki and multiprocessing really don't change across 1 or more nodes. It stays the same. So you notice that there's very consistent behavior between 1, 5, and 10 nodes for SVM random search, SVM grid search, and random forest. These are use cases for Loki and multiprocessing. And that's because they typically run on a single machine. And what you start noticing here, if you look at the rest of the graph, is that the performance varies quite a bit for Dask and Ray. And you see that the performance is very different for 1 node to 5 nodes to 10 nodes across these different scenarios. And there's quite a few reasons for these, and one of them is that Dask and Ray are pretty good at distributed computing. There is an artifact of this graph I'm probably not going to talk about. But one thing to note here is that for the random forest example, you can have a lot of performance improvement for algorithms that are very parallelizable. And I should note that because this is an integration with JobLib, integrations aren't always perfect. So there's always work to be done to further improve these results for more distributed computing settings.
I have a question for you.
Yeah. Yep.
So this is this might be a hard one. So the new Macs with the M1 Apple CPU have 4 cores and 4 low power cores. So 4 fast cores, 4 low power cores.
Yeah.
Would using all of these cores cause any problems due to half the cores being fast and half of them being slower?
So I would have absolutely no idea. If you send me that question, I can get you an answer because I work with people that are a lot smarter than me that work with those all the time. So I can get back to you. I'd be more than happy
to you.
Yeah.
Cool.
And by the way, you can reach me through Twitter at Galarnyk, MGALARNYK at anyskill.com or mgalarny@gmail.com. Anything you want to reach me.
And does your final slide have that on it too?
Yes, it does.
All right, great. We'll get it then.
And of course, if anyone has any questions about anything, feel free to reach out through any means. So I should mention that, of course, memory is always constrained. And so, for example, Ray has a high throughput decentralized scheduler along with shared memory, allow Ray to schedule or scale the workload to multiple nodes. So it's pretty good at managing memory, which is always a concern if you tend to parallelize or distribute workloads. And of course, one thing to note here is that these processes you expect to jump up a lot more from 5 to 10 nodes if you completely distribute your processing really well. But for a lot of programs, there's a serial part of a program that functions as a bottleneck, and performance is hard to improve from there. And of course, if you're curious about this, there's a link you can learn about distributing Scikit-Learn. And these slides, of course, are available online, and I'll share them in the description below. So I should mention about what Ray is, because I'm effectively using Ray as an execution engine here to manage workloads and distribute things. But Ray can be used for a lot of different things. It's an open source library for parallel and distributed Python. And there's an entire Ray ecosystem. There's core Ray system, there's scalable libraries for machine learning, and there's also tools for launching clusters on any cluster or cluster provider. So there's native libraries that are built on top of Ray, like RayTune, RLlib, RayServe, RayHDD. There's a lot of libraries that have integrations with Ray, including JobLib, which we saw in this talk. Dask has an integration, Spacey, MLflow, just a lot of different libraries. And if you're curious about Ray for some reason, it's a great library. I love it. You can go to Ray Summit and learn more. You can also go to AScale Academy. There's a lot of different places to learn more about Ray if you're curious and you want to distribute your workloads. So I'm now going to take questions and I'll answer them the best that I can. Of course, you can always reach me through my email or my Twitter.
There's something in chat if you want to look down at chat.
Let me see if I can answer it properly.
Sure. It's really just more of a guess to the previous answer.
Yeah. So
if you have 4 full power cores, jobs 3 or 2 might be best. And half of them, I mean, I don't know, but if half of them are half power, then jobs 3 might be better than jobs 3. I don't know. It's a good suggestion. So,
I mean, the answer here is really just if you have 4 power cores, jobs equal 3 or 2 might be best. So I think the problem here is I don't know how it interact with these different frameworks. So I'll ask and come back. So I guess try is the best, answer here. If you're curious about using, let's say Ray, for example, as a backend to do this sort of thing, you can always ask on Discuss for Ray. There's a channel. There's also Twitter. So you can ask as well. Also, Scikit-Learn might have a good page about the new Macs as well. Any other questions? It doesn't necessarily have to be specifically about all the stuff in this talk, things you might be curious about, literally anything.
I don't see any more.
Hey, this is Jeff. I have a question.
Sure.
So this slide you're showing right now, I had one question. So if I look at this, if I compare, say, Ray and Dask, right? I understand Dask is another distributed programming framework. So if I look at the SVM random search, it seems like they're pretty similar. performance. But if I look at the vector machine grid search, then suddenly Ray does a lot better, and same thing with the parallel training. Do you know why that's the case?
So there's a couple of things here. These are integrations. They're essentially using Dask and Ray as effectively backends. So integrations aren't always perfect. And so that's one thing. So it may not be the performance you natively get from, let's say, Dask or Ray, because it's integration with JobLib, which Scikit-Learn happens to use. So integrations are, just coming. For the random forest example, there's an issue on Dask GitHub about this actually. If someone wants to answer it, I think it has to do with memory constraints or the global interpreter lock, but I don't know. I can actually hold it up right now, the talk. It's so far beyond my understanding that if someone wants to answer this, by the way, that'd be great. So it's been an ongoing issue for Dask for a while right now. So it's been going on for a while. I think it's an interpreter lock issue, but I don't think it's the issue necessarily with Dask itself. I think it's more the integration with JobLib, which Scikit-Learn happens to use. But I can find out if you're curious.
Okay, well, that's cool. I was just curious if there was anything special that Ray was doing.
Oh, I mean, I think it's the integration's really good. I think Ray's also, I don't want to speak Ray versus Dask here because I can start it's more just an issue with that model itself rather than Dask itself, if that makes sense. Because SVM is doing pretty well for Ray and Dask. Performance is relatively similar, but for random forest, it's just an issue with the model itself. Yeah. It's like just, some bug essentially. Yeah.
Okay, I think we had one more comment from, I think it's just Dave's DM1 CPUS.
Yeah.
Okay, anyway, so if no one has any more questions, then I think we can wrap things up. So I don't see anything else. I want to thank you, Michael, for this talk. It was really great. I learned some things. I didn't realize you could actually parallelize training itself in Scikit-Learn. So that's pretty cool.
Yeah. I didn't know either until, not too long ago. So it was a very good surprise myself when I found it. These libraries are always improving. So maybe next week, it'll be even better than today.
Right. Yeah, it sounds like from my research on my website, I can see that you guys are checking a lot of code for Ray. So.
Oh yeah, mostly my team or the people I work